Hey everyone, my name is Omar Zoni. I'm one of the technical managers for the SOLIDWORKS simulation products, and welcome to another edition of the SOLIDWORKS Simulation Step Up series. Today we're going to be focusing on productivity tools. We're going to cover a handful of them. We're going to talk a little bit about Load Case Manager, Trend Tracker, design studies, as well as optimization. So we're going to be spending a lot of time in the software with this one. So hope you guys enjoy, and we'll touch base at the end. Again, thanks. So today's version of the Simulation Step Up series is going to be uh, around simulation-based productivity features. So let's go ahead and get started. Now, when we talk about productivity, what exactly do we mean, and what are we going to be covering in this specific video? And really what we mean is leveraging any automation that we can to make our lives easier. And then the first thing that we're going to look at is Load Case Manager. I'll get into more detail when we get into the software, but it's a way to automate. Potentially you have a model that has multiple linear static load cases that you want to subject it to, as well as potentially combinations. So this is a way to kind of automate that. Next, we're going to talk a little bit about Trend Tracker. Trend Tracker allows you to take a model and make changes to it geometrically, or to the material properties, and kind of monitor how those changes change things like factor of safety or displacement. You can always go back and a trend tracker run to any of the previous iterations. And then we're going to talk about design studies and optimization, which are really where you can start exploring your design space by specifying parameters that you want to be able to vary over a range or over a range with step, and allowing the software to kind of drive or dictate where the design should go. So let's start with Load Case Manager. Now, Load Case Manager is kind of it was introduced in about 2015, I believe, and it is a streamlined method of setting up models which have multiple load cases. Now, the caveat is that the load cases need to be linear static. You can combine the load cases, so if you want to combine, kind of load case A with load case B, you just have to be aware, right, that when you're doing those combinations, you want to make sure that you are not moving into the nonlinear realm. And you can utilize sensors to kind of monitor whatever values you're interested in, whether it's a stress on a part or a displacement, or maybe a rotation, a strain. Any of those values, you can create sensors, factors of safeties that you can kind of monitor during the load case runs. And this is kind of what the interface looks like. So let's go ahead. I'm going to hop into the software and we can take a look at Load Case Manager. Okay. So let's take a look at our first productivity tool, and that's going to be the Load Case Manager. Now what I'm going to do is I'm just going to create a new study here. Now again, remember that with a Load Case Manager, the assumption is each of your individual load cases has to be a linear static run. So I'm going to select the linear static study, and I'm going to create something called Load Case Manager. And you can see it's created a new tab here. Now my material property is fine. I'm going to make the assumption it's 7075 T6. The tricky thing, or the thing that's a little bit uncomfortable when you're first setting up Load Case Manager runs, is that you need to put in all of the potential load cases in the same study. So for instance, this model, I'm going to make the assumption once there's going to be a downward loading, same load value, but an upward type loading, a lateral loading, a torque loading, and then there are going to be some G loading, so a 20G vertical and a 20G side load. And then there are going to be some secondary load cases that we're going to combine some of those initial load cases very, very quickly. So let's first put on our boundary conditions. And we're going to add a few fixtures here. So one is going to be a fixed hinge. And we're going to apply that fixed hinge right here on this face. So that basically just means that that face can just rotate. Now there's another group of fixed hinges that we're going to take advantage of and apply here. And that's going to be these two. And then finally, we're going to make the assumption that this thing is actually butting up against another flat plate, and we're going to add what's called a roller slider. Now these boundary conditions are actually going to be in all of our load cases. So nothing different here so far. Now let's go ahead and start adding some of our loads. So the first load that I'm going to add is an external load. It's going to be a force, and it's a 2,000 Newton load. I'm going to apply it to this face. and it is going to be in the lateral or the up and down direction, which for us is Z. So I'm going to say I want to select the direction, and you've got a couple ways that you can approach these types of runs. So I'm going to pick the correct plane, which is that guy, and say that I want my load to be normal to that plane. Now you can see, right, it's applying that load in the positive Z direction. Now you can either put in the actual load value, and for this particular model, our upward and downward loading are both 2,000 newtons. So that's something very, very easy to do. But if your upward loading was, say, 1,700 newtons and your downward loading was 1,300 newtons, either you need to put in two loads, or the approach I often like to take is I'm just going to let it at a unit load here of 1. And I'll show you why, because in the load case manager, I can scale that load. And I'm going to go ahead and say, okay. Now I'm going to rename this just for myself, and I'm going to call this up underscore down loading. Now I'm going to apply another load, and it's going to be my lateral load, right? So again, on this face, but in a selected direction, and I will use my, what is that, my top plane to kind of define the direction of the load. You can see the direction there, and I'm going to, again, go normal to it. And I've only, for me personally, I always like to use a unit load factor. Now, if you talk to other engineers, they have different approaches to these kind of problems. You know, there's no right one right way to do this. So I'm, again, just going to use it as a unit load in that direction. And then the final load case, or the final kind of directional load case or directional force is, well, let me rename this first. I'm going to call this lateral. And then I will apply one more, and it is going to be a torque load. With the torque load, I will again pick my face. It's going to ask me for my axis. I've got an axis that's defined right here. You can see the torque, and it is a 50 Newton meter torque. But again, I'm going to leave it as a unit load. And I will redefine this. Well, I'm actually not going to rename it. I'm just going to leave it named as torque. Maybe I'll get rid of that -1. We've also got some G loading, right? So I'm going to apply a gravity load, and I'll leave it as a unit load, but the direction is wrong, right? So it's not actually relative to the front plane, and gravity is one that you're going to have to be a little bit careful with, because we're going to have to use some of these advanced options. So I want to make sure that I have a good understanding of exactly which directions I want gravity to act in. So obviously, there's going to be one case where gravity acts there. Now let me just make this 0 for a second, because I want to make sure that I understand which direction 2 is getting me my lateral loading. And it's not that one. It's actually the third direction, right? So it would be this one. And I'm going to leave it there as well as here. And I can zero those loads out at a future time, but at least I want to make sure that I understand that second direction is 0. And I'm just going to, I'll leave this as gravity loading, or 20, I'm going to call it 20 G loading. Now, with respect to the match, I will just create a simple mesh here. Not going to spend a lot of time on this. I'm assuming you guys probably have done some of the other simulation step-up series stuff. Don't worry about the quality of the mesh right now. That's not what we're focusing in on in this study, or in this, this step-up series session. Okay, we've got all these loads on here. Now we need to define our load case manager, right? So if I just come up here and right-click top level of my simulation study, I'm going to say, hey, I want to create a load case manager. And I'm going to go ahead and let me add my first load case. It's not going to be called load case 1. I'm going to call it downward loading. And all of my, like I said, right, all my boundary conditions are going to be there. I am going to be applying, I'm not going to be suppressing this guy, and it's not going to be a value 1, right? It's going to be 1,000. Now, the lateral load, the torque, and my G loading are all going to be turned off in this case. So that's all I need to do. Now let's define my second one. This is going to be upward loading. This one will not be suppressed. It won't be a 1, but it's going to be -2,000. Or I'm sorry, I have these back at -2,000. Sorry about that. I believe, and upward is going to be 2,000. Although, it doesn't really matter. We're just defining kind of up and down loads, but I've been a little bit more cautious about that when I initially set this up. All right, so we've got our first 2 load cases defined. Now let's add our next one, our lateral loading. We're just going to call this lateral. Everything is going to be 6 except my lateral loading. It won't be a 1. It's going to be 100 newtons. I actually believe that this one is 1,000 newtons, but let's put it in as 1,000. And then load case 4 is going to be my torque. Thing will be suppressed except my torque value, and it will not be 1, but it will be 50. Now I've got my 20G load cases, right? So I'm just going to add them both at once. We're going to call this one 20G ladder vertical. And again, all suppressed. It's actually going to be negative 9.81 times 20. So let me pull up my calculator. 9.81 times 20. It's going to be negative 196.2. So negative, let me just come in here, negative 196.2. And then for my load case 6, which is 20 side, our second one here will not be negative or 9.81, but it'll be 196.2. Got all my primary load cases defined now. Okay, so now let's add some load case combinations. So I'm just going to click here, and I'm going to delete these just for a second. You see when I delete those, it's asking me, okay, well, what do you want to do? What is your load case combination? And my first one is going to be downward loading. I'm going to do lateral. And you can see it's created combination 1. I'll just leave it called combination 1. My second one is going to be 20G vertical plus lateral. Okay, and finally, I'll just add one more real quickly. It's going to be 20G side load plus my downward loading. I'll say okay. And I've already created a couple sensors. Again, I'm going to assume you guys understand how to create sensors. Sensors basically monitor results during a simulation run. So I'm going to say I want to go ahead and add my displacement sensor and my stress sensor. And then I will go ahead and click run. Now, obviously, this will take a little bit of time, right? It's got to run through each of these individually. And then when it finishes all of the primary load cases, it goes ahead and does the load case combinations, right? So very important that we make sure that we have linear static kind of runs, right? We don't want to be going into large deflection, because then when we do this, the adding of the load cases, we're going to have some problems, right? And just like that, very, very quickly, it's done. Now, you could have created these all individual studies, but I've got now all of my results, right? So I can click on one of these guys. And look at my results. Combination number 1, combination number 2, combination number 3. I've got all of this data stored down here, so I know what my maximum displacement is. I know which load case gives me the worst one. It's a kind of load case 1 or combination 1 or combination 3. And I can see where my worst stresses are, right? That's going to be down. It looks like, again, combination 1 and combination 3, which are obviously combining our downward loading. So that's a very, very quick review of Load Case Manager. So now let's hop back into the presentation, and we'll spend a little bit of time talking about some of the other productivity tools. Okay, so we kind of covered the first one. Now we're going to talk a little bit about Trend Tracker. And Trend Tracker is a manual approach that allows you to monitor changes to a design and store each of those iterations, right? So it's useful if you've got a model that's undergoing changes that you can't easily set up in a design study, like maybe like adding an extruded cut through a whole body is something that we're going to do, or maybe adding a rib feature, or maybe there are other reasons why you would use it too. Maybe changing thicknesses. The nice thing about Trend Tracker is it always allows you to go back and go back to a previous iteration. And I like to call it kind of a poor man's optimization. So this is kind of some of the results that you would get from a Trend Tracker study. Let me go ahead and show you exactly what it looks like and how you would set something like this up. Okay, let's take a look at our second productivity tool, which is the Trend Tracker. So I'm just going to add a static study, and then I'm going to add some of my boundary conditions, right? And the boundary conditions are just going to be some fixed hinges applied here, as well as
to these two faces. And we'll just put on one very simple load. And that load is, let me just, yep, got them both. That load is going to be applied to this one face in a downward direction. So we're going to specify the direction. We'll pick the appropriate plane, turn on the normal direction, 2200. It's wrong, it's going the wrong way, so I'm just going to reverse it. I'll throw on a little bit finer mesh. I'm not going to go crazy. And we'll go ahead and run this guy. And what we're going to do after this thing finishes is this is basically going to be our baseline. So, okay, we can see our stress, our displacement, our strain results. I'm going to add a factor of safety plot real quick. You can see the minimum factor of safety is about 9. I'll turn the high or the max up to, let's say, 50. You can kind of see the factor of safety spread. What I'm going to do now is, let me just save real quickly. I'm going to define this as my trend tracker, or turn on trend tracker, I'm sorry, define this as my baseline. What that's going to do is it's going to add some sensors. So we can see our sensors that monitor mass, stress, and displacement. Now, if I also wanted to add a sensor that monitored a factor of safety as we went through this, I can say, hey, look, I want to add a simulation-specific sensor. It's going to monitor a factor of safety, and I want you to look at the minimum. And we can see that our factor of safety is about 8.661. I can add that value. I can add a tracked data graph here, and I'm going to say that I also want you to monitor minimum factor of safety. So you can see there's my minimum factor of safety. All right, now let's say I want to make a change to my baseline, right? And what I'm going to do is let's start by just maybe changing the thickness of that extrusion. So it's 16 millimeters now. Let me turn it down to 14 and rerun this guy. Now, if you're making these kind of changes, right, that's one that you could do with the design optimization pretty quickly. But I'm going to go ahead and add those values. And we can see exactly what that looks like, right? So how's my factor of safety changing? How is my mass changing? How's displacement changing? Got access to all of those. Let's say that still looks fine to me. Let's maybe turn it down a little bit more even. Go ahead and I'll rerun it. Changing thickness, again, that's something that you could really do pretty simply inside of a design study. But now let's say that I've looked at this and I'm like, you know what? I could probably cut out some of this center region, right? So let me go back to my model. I've got a sketch here, and what I'm going to do is just add an extruded cut. It'll be, through both sides. And now I'm going to go back to my study and rerun this. Now, how does that change my result, right? We can see the mass is really going down. So it went from 0.26 down to 0.13. I've cut it in half, right? What does my factor of safety look like? Ooh. So maybe, just for the sake of argument, let's say that I was shooting for a factor of safety of 4. So now I've got a problem, right? So I know that I can't cut the whole way through it. Maybe I can come back to my and add, let's say, maybe I want to add some of the material back, right? So I can go back to my model very, very quickly, add an extrusion. So I will pick my sketch, add an extrusion, but I am not going to do blind. I'm going to do I guess I am going to do blind. Let's just make it 1 millimeter. And I'm going to add a second direction because I'm not sure. Well, you know what? For the sake of just being quick and dirty, you know what? Let me add that second direction. So I'll add a second direction, also 1 millimeter. Okay. Now I've got my, that doesn't go all the way through, and I'll go ahead and rerun this now. Hopefully that will pull my factor of safety back up above 4. Take a look. And it did, right? I could probably even make it a lot thinner, as it turns out. So I'll stop here, but you've got access to all these results. There's a very nice trend journal that kind of walks you through what you've done at each step and how it's made changes. There's also a trend gallery that we can take a look at that shows me results for each of the iterations. So I can walk through this. So this is showing me how displacement has changed. My von Mises results, Factor of safety will also be shown. So, very, very nice and quick way to do some very, some powerful kind of design iterations. So something that you should take advantage of if you have.
And finally, we've got design studies and optimizations, and I kind of group them together because the interface is basically the same. And this is where it really allows you to automate the exploration of your design space. What does that mean, right? It means that you can evaluate geometric changes, material property changes, simulation values like forces or any applied loads that maybe you want to run a sweep and see how that changes displacements or stresses. Doesn't have to be linear, can be nonlinear in nature, can be across different studies. And the nice thing is it's very powerful if it's utilized correctly, right? You can do optimization techniques which basically allow the solver to kind of dictate what your optimum design is going to be based on some criteria like minimizing mass. And you have your kind of convergence criteria for the optimization, and then you have your check criteria like your factor of safety needs to be above 1.5, or displacement needs to be below this, or temperature needs to be below this value. So let's go ahead and take a look at that now.
So let's take a look at our third and fourth productivity tools. And their design studies as well as optimization are kind of intertwined the way you set them up. So that's why we're going to look at them kind of as one. And we've got a real simple example here. It's just a heat sink. The heat sink has got a heat flux applied on these back two faces of about 2,000 watts per meter squared. It's got convection defined on all of the external faces, 8 watts per meter squared Kelvin, and room temperature basically is the ambient temperature. And this is our initial design. You can see that the maximum temperature in this initial design was about 63 degrees. Now, we had a customer that came to us with this problem, and they knew that they were making, tens of thousands of these heat sinks. They knew that the maximum temperature could go all the way up to 76 degrees C. So they were pretty confident that this thing was over-designed. Now, they couldn't make any changes to the back face here, but what they could change, and this is the reason why I'm explaining this to you, is because if you want to use this tool, you have to kind of understand how you're going to explore your design space, which is really what we're doing here. But what they could change was anything related to the fins. So what we did is we created a design study, and we labeled it thermal optimization, and basically all of the geometric parameters associated with the fin, we created kind of like a variable for them. So you can see, for instance, the fillet of the fin. And we said that the fillet can go from 2 to 20. The depth of the fin, which is this dimension right here that's now 50, could go from 26 to 50. Same thing with the height. The number of fins we said could go from 20 to 60. The thickness of the fins. And we define them as a range, which means that basically they could be any value in between that range. Now, you don't have to define it that way. You can define it as a range with steps. So you could say I want it to be 20 to 60 in steps of 1 for the number of fins, which would probably be a little bit more accurate. But if you want to do an optimization, you kind of have to leave it as range because it wants to be able to pick anything in that range in order to figure out what the optimized result is. You can also do discrete values, right? So if you knew that you wanted the thickness to only maybe be a quarter an inch, a half inch, in very, very discrete values, or maybe, a quarter inch, 1 inch, 2 inches, it's something that you couldn't do with a range with step. Now, for your constraints in a design study, basically what I've done is I've created a sensor that monitors the maximum temperature in the heatsink when it's run, and it points to the thermal one study, or the thermal run study, which is basically where I set up and run my thermal analysis. So you could actually set these up to run over multidisciplinary, right? If you knew that the heatsink had to have a certain frequency that it was above, resonant frequency, a certain displacement it couldn't exceed, you could start creating multiple constraints that pointed across different studies in order to, really gain some more insight. And then my goal is I've created a sensor that monitors the mass, and I want to minimize the mass. And what this does then is it runs through and creates a design of experiment. And based on the number of inputs, that's going to determine how many steps that it takes. Now, as it's running, let me just click on one of these iterations, for instance. I have access to all of these results. Now, any of them that are gray, any of the iterations are gray, you can see that my temperature is under 76. Now, for iteration number 6, we can see my temperature is above 86 or 76. So any of them that are red means they didn't meet my constraint. And then when it gets finished running, it looks at, kind of like the slope, or how each of these design changes is kind of affecting your constraint, and it gives you what it feels like is the optimal result. And in this case, you can see the optimal result looks like this. Here was our initial temperature of about 63. And here is our optimal temperature of almost exactly 76. But look at the difference in mass, 4,300 down to 2,500. So we cut about 1,800 grams of mass out, which, if you're making tens of thousands of these, it's very, very important. We also have the ability to look at graphs. So if I want to get a feel for, exactly how the number of fins is controlling the temperature, I can do that. I can manually slide this thing back and forth to get a feel for exactly what it looks like, what the result's going to look like in that configuration. So again, you can create, kind of local trend graphs. You can create design history graphs. So I can say, look, I want a local trend graph where my X value is going to be the fin thickness, and my Y value is going to be my constraint, which is temperature. And I'm going to localize it at my initial. And we can see exactly how the fin thickness is controlling things. So you can see it's a very complicated kind of multi inputs, and then we can come up with what our optimal design is. Now, the only difference between design studies and design optimization is I could just turn off optimization, and if I did that, it would just go through and run all of those steps, and it would be up to you to figure out what, which design is the best. So, and again, if you're not using range, like if I was using range with step or discrete values, they tend to be situations where you wouldn't be doing an optimization, but you can actually do optimization for any of those. So again, that's kind of design studies and optimization.
All right. Well, thank you guys for tuning in to this session on productivity tools available inside of simulation, specifically around kind of design optimization, also with Load Case Manager, though. My team is having a really, really nice time generating these videos, kind of rebranding this the Simulation Step Up series. If there's anything that you feel like we're missing and that you would like to see included, please, feel free to add a comment to any of the social media that you might be looking at this on. Reach out to your resellers if you guys need further explanation or there's something else you'd like to see. And thank you guys for tuning in. Look, check out, continue to check back because we'll be updating this content pretty regularly.